Hello everyone, this is Kumar from Department of Chemical Engineering from Weltech Tech Dr. Rangarajan and Dr. Shakuntala Engineering College. I hereby present my final year project named Optimization of Delayed Coker Unit and Coker Furnace. This is Kumar along with Dilly Ganesh. We are presenting the final year project report along with our internal guide Dr. J.B. Veeramani, Head of Department, and our co-guide Mr. S. Madasamy from CPCL. The project abstract here is a plot made to improve the performance in the heat exchanger in delayed coker unit. Along with in heat exchangers, we have increased the diameter in heat exchangers in order to reduce the fuel consumption to avoid pollution. This design here claims to give an improved overheater structure performance by migrating of the hottest part of the process fluid to the upper portion with a lower heating rate. The main objective here is by using existing residue conversion, by changing the existing residue conversion, which are currently they are using this following residue conversion solutions, which are visc breaking, solvent deasphalting, residue hydroprocessing. As I said before in abstract, we are using these methods to make the maximum yield, which are as follows. One is this, by using slurry hydrocracking method. Another one is using increasing the diameter of the heat exchanger, and other one is the improving the delayed coker unit furnace. In this project we are concentrating on increasing the diameter of the heat exchanger, also in improving the delayed coker furnace. So in delayed coker unit, the main process consists of heating a residual oil field that is coming out from the refinery, which is the bottom product, to its thermal cracking temperature in a furnace with multiple parallel process. So we are getting a product of petroleum coke and gas oil. Delayed coking is one of the unique process used in many oil refineries. This is the flow diagram of the actual delayed coker unit diagram, where you can see a delayed coker unit, a fractionator, and a coker heater. By heating it at different fractions, we are getting the products which are as follows: naphtha, diesel, slurry water, wet gas, rich absorption, lean absorption oil, heavy gas oil, and etc. This is the estimation of the feed alongside of the product, so that as you see the feed here, the feed here is the clarified oil, PDA pitch, feed from 3 refinery columns. We are getting the main products like LPG, light naphtha, heavy naphtha, light coker gas oil, heavy coker gas oil, so that to balance the product output. This is the existing equipment design. As you can see, these are the changes. Then as I said before, to improve the diameter of the heat exchangers, so that these are the design calculations from our project report. The design calculation is mainly depends on the shell and tube heat exchangers. As you can see, the tube side we are getting the heavy coker gas oil and as hot fluid, and these are the some values to help us to predict the actual area and the length to be precised for future revamping of the heat exchanger column. We are using first of all we are using LMTD to calculate the differences in temperature, and thereby we are finding the heat absorption and the area need to be covered and the length to be revamped in the shell and tube heat exchanger column. Another method, by increasing the coker furnace length. As you can see here, the coker this is the structure of the blast coker furnace used in the refineries. We have to to improve the coker furnace length. First, we have to analyze. By analyzing it, we can improve the coker furnace length. As I said before in the abstract, the coker furnace length to be increased by means of a coker furnace rod, which is made up of mild steel, so that we are taking the somewhat CFD simulations to tally the coker furnace length. These are the factors that are included in the coker furnace, which are as follows: comparison of mean temperature rise rate between actual and the model predictions, TMT rise. Here the run length if we have the run length is the main factor. It decreases with the increase in all parameters: process temperature, flow rate, and feed asphalting content. It can be seen that the non-uniform temperature can lead to localized high rate of coking and can limit the run length of the furnace. Thus, it is necessary to maintain the uniform temperature along the length of the coker furnace. These are the downflow or upflow configurations predicted by using the simulations. First, we are seeing a heat flux ratio versus bulk temperature ratio in downflow and upflow configurations. Downflow and upflow. We are going to see here. The figure, as I said before, shows the variation in the heat flux across the tubes for both downflow and upflow configuration in the radiant section. The ratio of the heat flux of an individual tube to the average heat flux in a downflow configuration versus the non-dimensional bulk temperature. In a downflow configuration, the heat flux is the highest in the exit and the lowest at the inlet, whereas the process flow is reversed. And in an upflow configuration, the opposite occurs, with the tubes at the exit experiencing the lowest heat flux. In figure B, we are comparing the TMT for both configurations at an SOR analysis. TMT is represented here, and the TMT at SOR for an upflow configuration at the bottom tube is lower at the top. It increases compared to a downflow configuration. TMT are higher in the majority of tubes compared to the downflow configuration. Similarly, in figure C, we are comparing the rate of temperature rise to maximum TMT in down and upflow configuration. Here, the same is reflected in the TMT profile, where the rise in TMT is lower in an upflow configuration compared to the downflow configuration. It should be noted that the increase or decrease is with respect to the baseline in the heat considered in this study. And finally, here we are discussing. Here we are concluding the project by saying that by increasing the heat exchanger to an existing area to about 49 centimeter more, we can optimize the delayed coker unit function. As you can see here, existing equipment has an area of 161.6. We are revamping it to about 49 meters, so it can be used as a better solution to optimize the delayed coker unit function operations. Cost estimation here: the initial cost of fitting new heat exchanger or revamping the equipment is initially high, but the operating life can be exceeded. It has high efficiency also. The model that we have predicted in simulation to increase the furnace length was developed wherein different modeling and simulation tools. The developed tool can be used to evaluate various possible options to debottleneck the existing coker heater. Thank you.